Hi everybody. First I apologise for this slightly bit for this talk. So I'm still recovering from the flu. The corridor where I sit is fully decimated with everybody that's ill at the moment. So if I have to stop and sneeze, etc., I apologise for that. So my name is Professor James Covington. I'm an academic from the School of Engineering, University of Warwick, and I'm based in the UK. And today I'm going to talk about our work on our IEEE P2520.1 standard. So I'm the P2520.1 IEEE Standards Association Working Chair. Troy has given kind of some introductions about the Standards Association. And kind of what I want to do today is talk about our efforts to develop this standard, some of the issues, and then go through some of the basics of how the standard operates. So I've been at this 5 years. I still remember starting this standard in 2000 in Starbucks near my mother-in-law's house, because it was just about to be COVID and I couldn't visit her. So it's taken us 5 years to get to this point. So the other thing is that this is one of two talks. So I'm going to talk about the general overview of the standard, and Edouard will come after me, and he's actually had a go at the standard. So the idea is that I'm going to talk about the kind of high level things and some details of the standard. Then Edouard is going to talk about his attempt to complete the standard. Okay? Oh, is it going to let me rotate around? Okay, cool. Right. So what can I say? So this standard is really based around the development of something for olfactory devices. So the electronic nose and machine olfactory arrived in the 1980s. We could argue about that date, but since this was work that was done at Warwick with George Dodd, I'm going to take that this is the 1980s. And George and Christian Prasad were interested in developing systems that replicate the biological olfactory system. So, you know, we're now kind of 40 plus years on from that work, and we're still working, or lots of researchers are still working on olfactory devices. So one of the big issues has been throughout that period is there has been some work undertaking comparing devices, but there's very little still that kind of compares different products and sensing. So if you're a commercial company or an academic partner or company or somebody, and you were going out and you wanted to, you know, look at different electronic nose or machine olfaction, it's very, very different to compare them. You know, there has been some work. So Troy did a lot of work in actually the 90s with all the electronic noses and comparing them. There's some really good work happening in Europe on standards, and particularly the VDI stuff, in olfactory devices and machine learning. That's really good stuff as well. So there are kind of some attempts to develop standards. However, in most cases, this is still working in progress. So this to talk about is our attempt to create this standard. Okay. So kind of coming to olfactory devices, one of the big issues is really talking about what, you know, how do we mimic human perception? I think that some of the previous talks are really good at talking about this, but, you know, we still really haven't answered what is an odor. And if you imagine that you're using electronic noses, so you're using an instrument that's created from an array of gas sensors, these sensors may not respond to, you know, the odor. They're responding to specific gases and volatile compounds within it. So it's very difficult to kind of relate an array of gas sensors that they're doing kind of some pattern recognition to a specific odor. Okay, so we don't have all the answers to this. This is still a really difficult problem. You know, one of the kind of issues is that you might get small variations in an inorganic gas like carbon monoxide, and that will change your sensor readings. So the odor intensity, you know, as human perception will stay the same, and you get these kind of small variations in other things will affect it. The other big issues is that sensor detection limits and human detection limits are very different. So humans' perception of different smells changes in orders of magnitude based on the chemical around it. So some things they can detect it in crazy, crazy low concentrations, and other molecules they can be really, really high concentration before they get to it. And then things like odor intensity. So, you know, humans don't detect linearly. They don't have variance between them. So what the sensor is detecting in terms of chemical intensity, it could be very different to what the gas sensor is detecting in Tesla. So this is kind of some of the things that have been affecting the field and the development of standards for a very long time. So, and I kind of put this thing, this slide in because this is kind of a big thing that, you know, and other efforts to develop chemical standards, or sorry, machine olfaction standard kind of hit this problem. So, you know, in one camp, you have loads of people that think that we should be testing these devices in real life conditions. And at the other side, we've got people who are arguing, oh, you know, we must go test this with verified test gases. And there's this kind of competition, not competition, but this kind of battle between these type of groups. And I know that there's been attempts to develop standards in the past, and this problem never got solved and the standard failed. So I think this is a really overarching problem that we as a group or as a community haven't totally sorted. So how we've decided to attack it is through a family of standards. So if you kind of go try the IEEE things, you can go look at these. So how we've got it is there's actually about 30 standards we're proposing in this P2520 family. So the P2520 standard family is like the parent, and then below it is its kind of children things and all the substandards. And then the first standard, which is what we're talking about today, is P2520.1, which is a baseline performance standard. So the idea is that you do P2520.1 first, and then once you've passed that, you can go and then pick your specific standard. And these are just some examples in, you know, outdoor nuisances, indoor, industrial applications, medical, safety, etc. But the key thing is that P2520.1 is a baseline test verified standard, whilst the others will be real life conditions. And this is our attempt to how we solve this problem of, you know, real life versus lab-based tests. So these are, some of these are in development at the moment, and if you kind of email me or the IEEE, you can kind of become working groups on some of these. Okay, so I thought I'd kind of cover some of the technologies that we're going to use in the standard. So there was a lot of discussion about what we were going to keep and what we were going to reject out of it. So the thing is that the term electronic nose or machine olfaction is a really, really broad term because it's really about a method approach. It's not about a single gas sensing technology. So we tried to make it both all-inclusive and slightly selective. So, you know, when the standard's released, you'll be able to read this in more detail, but basically anything with kind of a gas sensor array, such as, you know, electronic noses as kind of traditional thing, they're covered by the standard. Lots of physical measurement techniques, so things like IMS, optical, NDI, SPR, they're all covered by the standard. There's also things where if you have a single sensor or a single detector, if you can tune those parameters, so you basically create like an array of virtual sensors, they're also covered by the standard. So a good example would be a MEMS-based metal oxide gas sensor. You could go through a thermal modulation approach, and you could use, you know, static or dynamic temperatures, and they could become virtual sensors. So all of that is covered in there. There's a little bit of portable mass spec and NMR in there, but it's a bit more limited. But the other things that we allow is any form of pre-concentration. So if you want to use a absorbent tube system, SPME, that type of thing, they're included, and then kind of pre-separation technologies. So the most likely pre-separation technology would be kind of GC based to kind of separate out odors into more individual chemical components. They're all covered. So what's not covered is single gas sensor systems. So if you have you know, if you're interested in a CO detector, like a portable CO monitor, and it just gives you a CO reading, that's not covered by the standard. Even if you have, let's say, a unit which has 4 sensors, but you're basically measuring individual gases with those and just using them 4 individually, that also isn't covered by the standard. Other things that aren't covered is things like GCMS, PTRMS, SIFTMS, etc. So kind of high-end analytical instruments that you see in kind of lab bases, none of those are included in the standard. So there are other mechanisms for that. So, I mean, there was lots of discussion around, you know, if it's like a field portable device, that's generally okay. you know, if it's an air-based using air as the carrier gas, that would definitely be covered, etc. So we've tried to, you know, separate off those kind of high-end analytical instruments and focus more on kind of traditional electronic node stuff. So there was lots of discussion about the kind of what our ethos was for this. And, you know, like I said on the previous slide, we really want this to be universal. So we'd like it to be applicable to basically all or almost all odor and VOC analysis devices. So these are currently available, will be available. We would like it to cover all those type of things. We really would like it to be easy to implement, okay? So if you think about it, I mean, we cover academics and companies later, but we would like it to be used in universities. We would like it to be used in companies. We would like it to be used extensively. And some people are not going to have really, really expensive gas analysis systems, gas development systems. They're not going to have permeation tube systems and things like that because they're really expensive. So we develop the standard in a way that it's accessible to lots of different people with different levels of experience and different levels of infrastructure. The other thing we've done is that we have device and test chemicals. I'll come to that a bit later. But everything that you need to complete the standard is easily accessible. You can go out and buy them, relatively simple at the required concentrations you need. So it's not difficult to actually get the test chemicals for the standard. The chemical options are generally quite low risk. We've tried very hard to select chemicals that have a low health risk for the people using it. And in fact, we've defined some of the concentrations to be at kind of health and safety limits. The other thing is, I know this sounds weird, but we really would like it relatively easy for people to pass. So we want people to use it. So remember, it's a baseline standard, so we don't want to make it too difficult. We want people to use it. We want people to pass and then kind of publish their results, etc. So kind of a dream world like in academia is that a student project develops electronic nodes, they use the standard and then publishes the standard data in something like papers or an appendix or something. So the other thing is that it's designed for loads of different introduction methods. We actually wrote a big appendix to kind of give people ideas about how you could do the standard. And these cover things like auto sampling, gas flow systems, bags, etc. And we're going to make some specific documents for specific machines to explain how to use those and complete the standard. Okay, so the standard comprises of 3 levels. So level 1 is differentiation. Okay, so this is a very standard basic test where you have different chemicals and you are trying to show that the odor analysis device can separate these 3 chemicals. Okay, so it's very, very simple. It doesn't matter what those, you don't need to identify the chemicals at this point. You simply need to show that those 3 chemicals are different. The second thing is recognition. So in this case, you'll get your electronic nose, for example, you would train it with your chemicals A, B, and C, or A, B in this case, and then we would use the test samples as unknown samples, and you need to identify them. So you could, for example, the day before, you could run lots of tests. You could train your machine to know what chemical A is, what chemical B is, what chemical C is, and then you start the standard the next day and say, well, here are the test chemicals, which are A, B, and C. Can you recognize them? And there's some kind of values around that kind of recognition process. The final bit of the standard is quantification. So in this case, you are going through a range of chemical concentrations for your test chemicals, and then you have to basically have a true value, which is what you're presenting to the machine, to the predicted value of the machine. So as before, you can go train it as much as you want. You can run lots of practice samples. You can run test samples. You can create your calibration curves. You can do all of that first. And then when you actually do the standard, all the samples in the standard are unknown. But you can do any development technique you want, any model technique you want, etc., before you go for the standard. So the standard for both levels 1, 2, and 3 are basically almost seen as unknown samples because all the training, all the quantifications happen beforehand. So what does it think? So, okay, the end of the appendix, sorry, the end of the standard, there's an appendix. The appendix gives you a list of test chemicals. So these test chemicals are grouped into, there's 5 groups. and within each group there are 3 chemicals. Some are based on things like gas cylinders, so you'd have a standard where you can go buy 3 gas cylinders to complete that group of chemicals. Some are based on liquid. We do not tell you which group of chemicals to use. That is totally up to you as the operator. And in fact, as you go through the different levels, you don't have to use the same chemistry group every time. So if you want to do level 1 with gases and level 2 with liquids, absolutely fine for us. Okay. So you go along, you have a look at this appendix, you pick the group of chemicals that you want to do. So you select that group, so let's say group 3. And then on that, it has a concentration range. So we only set the maximum concentration you can use for that standard. So often you might go, well, that will saturate our machine out. We'll go for half of that or a third of that. That's fine to us. So we don't set the absolute concentration. We only set the maximum allowable concentration based on health and safety limits. So you can basically decide what concentration you want to use for these kind of different tests. So in differentiation, you get your 3 chemicals, we call ABC, and they're fixed at 1 concentration. You run a number of repeats of that. You then change the temperature by 10 degrees lower, run some more tests. You do 10 degrees high, and you run some more tests again. So you get basically 3 temperatures with those 3 sets of chemicals. You do the same thing again for different humidities. So you do 20 degrees, 20% lower, 20% higher than the kind of normal, and then you kind of combine that data together. So you do all these kind of 3 times, so each one is 3 tests, and then we ask you to repeat the test over a period of time. So for example, you might do this day 1, give day 2 off, run it day 3, take day 4 off, and then do day 5, for example. So it will take a week to complete the standard. But Etmar will come over that in a bit more detail. So for recognition quantification, for level 3 only, we do a concentration ladder of 5 different concentrations, and then you kind of have to work what those are. And then for the rest of the standard for 2 and 3, there's only 3 concentrations. And then we go through this repeated process at different temperatures, humidity, etc. Again, these are all repeated 3 times with time between the tests. So one of the things we do allow for level 2 and 3 is that if you run, for example, you do all the testing for level 3, you can use that data for level 2 if you want. So you only need to do 1 batch of experiments to pass level 2 and level 3. So this is kind of thing that you might get, for example. So this is one of our electronic noses. This is a Alpha Fox. So, here is a sensor response. We would use one of our test chemicals, chemical A, say, and you get something like this. You're allowed to do any type of feature extraction you like. So here we're just doing like a differential change, and you get something like this. And then you would do clustering. Sorry, my brain's gone soft. So you can cluster it any way you want. You can do, but it has to be unclassified. So you can use PCA, but you couldn't use something like LDA. Sorry, so non-supervised techniques. And so you get something like this in the test chemicals. So this is us having a go with the standard. So for level 1, you have to do this thing called a silhouette coefficient, and basically you have to score a certain levels. And if your instrument's able to score a specific silhouette coefficient, you pass the level 1 standard. For level 2, you both have the silhouette coefficient, and then you have to show how many of these you identified correctly. We do not define what type of modeling you use, what type of classifier you use, or anything like that. Though you have to state it, the standard is agnostic to identification approaches. So for quantification, it could be something similar. So you might have your sensor responses, you might do feature extraction, then you'll do some kind of concentration, quantification of that, and then we'll do a make concentration. So it's basically how accurate this is compared to the predicted value. And again, we give different pass-fail criteria for make. So when you see the standard, it talks about how to undertake the tests, and then at the end there's a table that says, for level 3.1, you need to do get a make value of, I don't know, 50% or something like that. So the standard is specific on what is the pass-fail criteria for these. Okay. So People are kind of working in machine olfaction for almost 40 years. I haven't been there at 40 years, possibly 30 something, but not 40 yet. And P2520 is kind of our attempt, so the US and the UK's attempt to create some standards in olfaction. So I know there's some previous attempts of this. I know the Europeans do some really great work as well, but this is kind of our attempt at trying to arrange a standard for machine olfaction. It has been a total pain. The challenges in olfaction have been considerable and still remain so. But we think that using this kind of dual approach where we use lab-based for the beginning first bits and then we do field testing for the substandards kind of helps resolve some of the issues with it. We hope that this will kind of, make it more easier for people to use them. So we've actually just about finished the standard. I think that we will go for an initial ballot in January 2026. Takes about 6 months from there. So we are hoping that the standard will be released in 2026. However, once we start the balloting process in early 26, you'll be able to access a draft copy of the standard. It's made public. You can go download it. You can send comments back on it, etc. So please keep an eye out for this, and I will the kind of working group will send out links to people so you can access a copy of the standard. But we really, really would like it to be used by academia and industry. It's written so that it's very accessible to companies. It's very accessible to academia, and we're hoping that everyone will use it. Okay, so I'm just about to finish. So the next talk will go through the application of the standard. And if you would like more details, there's a white paper on it as well. And basically, I'd like to thank all the P2520 team for their work. So there's lots of people here today, Edouard, Carlos, Troy, Susan, who have basically spent many years listening to me ramble on in project meetings. So I'd like to thank them to the bottom of my heart for their time and effort. So as we had a little bit of extra time, I would like to also plug ISOEN 2026. So ISOCS, which is the International Society of Chemical Sensors, is one of the big organizations that deal in machine olfaction, electronic noses. And ISOEN is our big conference, so it's been around for more than 25 years. So I will be going. It appears that I will be giving one of the keynote speeches as well in there, and I'll probably cover a lot of this work on standards and how we're getting on within that talk. So go have a look at the website, etc. The deadline for initial papers is either the 15th of December, if you will thingy, or if you want to kind of just go thing, it'll be later. So thank you very much.
Thank you, James, for your overview about the standardization efforts.
That's okay.
There are several
oh no, really? There's not questions, are there?
I don't know if we have time for all of them, but we can start from, for example, this one. How can we join the working group?
Okay, so if you email me, so is my email on the agenda, or just search for me. So James Covington, Warwick University. If you email me, I can then send you details about how to join the working group. So just to say that there will be lots of working groups starting in 2026, and you can pick what you like. So there might be one that really interests you. So I'm going to go do landfill after I finish this baseline one.
Okay, so if someone is interested, send via an email. Okay. Okay. And maybe the last question. Did you carry out any validation procedure of the methodology proposed?
That's what this talk is. There you go. That's a great question, Francesca, because I can say Edouard will now talk about his validation of the standard and method.
Okay. There are additional questions, but maybe it's better to, if you can remain here to discuss during the roundtable, since, okay.
Yeah. Thank you, everybody.
Thank you.